Okay, let's talk about an example that they give us where they perhaps give an unknown electrode but give the cell voltage. And once again, how do we do these? Well, we draw them and we can use our logic to find out what is what. This is going to be, suppose that we are given. Okay, let's just make a note here. Let's say it's an example. Okay, we are given an electrode. An electrode is made of tin. That's a new one. And the other is unknown. All right. The voltmeter reads, or a voltmeter reads 0.62 volts. Okay. And the electrons flow from the unknown. Okay. What is the unknown electrode made of? What is the unknown electrode made of? Okay, this is one that's in every single textbook, virtually every paper. There's a question sort of like this. Okay, where they've told us, and how do we do it? We said draw it, make a drawing so that we can logic it out. So let's say, all right, here we go. There's our unknown electrode over here. Doesn't matter which way you draw it, and the voltmeter goes that way. And they say the electrons, right, they do this kind of thing. All right. So therefore, they say that the electrodes flow from the unknown. So they didn't say which way, but this is the unknown. So the electrons are flowing that way. Okay, which means that the electrons are flowing from the negative to the positive. So we can say straight away, you are the unknown, therefore it must be negative, because the electrons are packing on there and flowing from there to the positive. So I can say you are the positive, right? At this side over here, right, the unknown is negative, okay, and they've told us that tin over here, this is positive. So we're going to go, let me just get out my my table over here, which is in the back of every single one. And here we go. Now let's have a look. All right. I've used here, we've got our table. So we've said, right, that this is tin. So they've told us the electrodes are flowing this way. So straight away, this is our tin electrode. So we can say, over here, what is actually happening? At this point, the Sn plus 2 electrons is forming Sn solid, correct? Because over here we had Sn plus 2 and it's going there and it's forming the solid. So this is now our reduction, isn't it? Reduction means this is the cathode. On the other side of it over here, we've got the unknown, right? But the unknown, this must be the anode, because over here I must have oxidation. That has to be true because it's the opposite of that. So at this stage, basically we've got this one is dissolving, isn't it? So we've got that guy dissolving. And we know the voltage was given is 0.62. Well, so far so good. The only formula that we're aware of here is that E of the cell is equal to E of the cathode minus E of the anode. And they've told us the E of the cell is 0.62 volts. The E of the cathode is minus 0.14 volts minus E of the anode. Because the cathode over here, they told us that this was, well, no, we've looked it up. Sorry, this is minus 0.14 volts. Okay, because we can look that up on our table. And we go to tin and we see Sn, where are we? Sn is minus 0.14 volts. Okay? Therefore, I can take this over, then it becomes 0.76 volts is equal to minus E of the anode. Therefore, I can take it the other way and say, right, therefore, let's just go over. Therefore, E of the anode must be equal to minus 0.76 volts. Then I go to the table. Now look it up. Look it up. Because we know that this is that. And we go to 0.76 volts and we see it is zinc. And in this case, the zinc solid is moving towards Zn plus 2 electrons. Okay, and that is our oxidation equation, right? Oxidation happens over there like that. So yes, that's how we're going to do these characters. Remember, you can do it from logic. You don't have to try and memorize. All you need to know, oxidation, anode, which is the one, it's shown in the table. That's the reduction one. You just need to know the basic structure of the copper zinc cell, which way the electrons are flowing, don't you? That's all you have to know. And from there you can work any single one out that you need to. Let us now have a look and say, right, let's have a look at some of the protective issues, some of the other issues of electrochemistry over here. All right? And this is generally a lot of theory, so we're just going to talk through it from a scientific perspective, right? So let's have a look at some practical issues. First one is corrosion protection. All right? Corrosion protection, what am I talking about? All right? If we've got a metal, all right, we've got an iron pipe, okay? That's a solid. Now, if an iron pipe, let's consider an iron pipe, and our iron pipe is, let's say, in the ground. Doesn't have to be. In the ground, not in the goud, but in the ground. All right? So it's getting wet. Right? And there are salts. Okay? Loads of them. Carbonates, sulfates, chlorides. Loads of salts in the ground. Okay? We could also have a pipe. We could also have a bridge structure here. What we find is that Fe solid does this. Okay? Fe plus 2 electrons. Okay? So this actually, if you like, it starts to dissolve. It doesn't it? It goes to an ion form. And what we find is that we introduce air into this as well. Air, which is O2. All right? Now O2 does this. O2, not Q2. O2. Okay? These are equations that in your books. Okay? 2H2O plus 4 electrons. All right? Goes to 4OH minus. This becomes the cathode. Okay? All right? This here is our anode. So you can see that if I've got here, all right, I have got here a situation where we've got air, and let's put in some rain. All right? The oxygen in the air with the water, look, oxygen and water, is going to go to an OH. And I've got up top there, I've got a cell where my iron is starting to dissolve. Essentially what happens over here is if you look up the voltages, all right, I've looked them up and you get minus 0.44 and this one is plus 0.4. Therefore the E of the cell of combining these two, all right, is going to be equal to 0.4 minus 0.44. Can you see? Which gives me 0.84 volts. And it's 84 volts. It's positive. Therefore, it's spontaneous. It's a spontaneous reaction, which thus means that, let's just take it down, if we've got this here, okay, we've got iron lying in the water and the air, I am going to get an electrochemical reaction between the two. It's going to spontaneously start to dissolve, and this is obviously where we get our rust happening. Okay? Now, let's just have a look. Okay? We want to prevent this. Obviously, we're looking to prevent this. So this is what we call corrosion. Okay, rusting. It's kind of fatal for a bridge or a pipe, because as this starts to, you've seen it, it's like a brown scaly stuff, and if you flick it, it comes off, and eventually that pipe is going to burst. For a bridge, slightly more catastrophic, a member fails, and then we end up with a bridge in the river. Now, under this situation, we want to stop the corrosion. Well, what can we do? Well, what we do is we want to make sure that we've got this reaction, Fe plus 2 electrons. Let me just turn it the other way around, because we've got the Fe solid going to Fe plus 2 electrons. We've got that. Now remember what we said is if we turn that around, all right, if we turn it around and we look, okay, because this here, all right, is our loss. If we turn it and look higher on the table, if we look above, these will rust first, won't they? If you look on the table where it is, the ones above it will rust first. So what we could do is we could say coat the iron with, say, zinc, because zinc's going to rust before the iron. Okay, it's higher up on the table, isn't it? All right, react with the cathode before the iron will, they'll rust first. Magnesium, aluminium, zinc are above. So we can use also magnesium, aluminium. These are all above. So they will rust first before the steel. Now, that's a little bit of a problem with aluminium, because aluminium is expensive. We'll see that when we look at the smelting of bauxite. The aluminium is expensive. Zinc, however, is pretty cheap. Okay? Magnesium also cheaper than a burst pipe. So what we can do is we then make the other one. Right? We make the other one the anode. So we say, all right, zinc, solid. We'll make you the anode. Whoops, I almost wrote in iron there. We make you Zn plus 2 electrons, because this one is above. This is an anode which is above the actual metal, above the actual metal to be protected, which means it's going to go first. We call this a sacrificial anode. All right. Now, what we do is we for example, if we have a pipeline, okay, here's my pipeline, long pipeline, right? And what we do is we bury blocks of magnesium alongside it. So we bury a block of Mg over here and connect. Further along, another block of Mg, further along. So these now become our anodes. All right? They're electrically connected. They are going to go first. I can dig this block up and replace it every 10 years or whatever. And yes, we can do calculations, all right, to see how long that will take to corrode. So the corrosion protection, you can also put on a coating Okay, we don't do those calcs. Let's leave that to the chemical engineers to do it. So we can also put on a coating, okay, of zinc. Okay, that's what we can do. So our process is to find something else that is going to corrode first. You must have heard of the thing with the steel bridges across the world and things like that. When they get to the one end, they have to start painting on the other end again. So that's rust proofing. That's putting a coating on it. Okay. That also, what we do is by putting that on, is we prevent, in essence, the water and the oxygen from getting to the metal in question. Aluminium is also going to corrode. Pretty much anything is going to corrode at the end of the day. All right. Let's now have a look, just talk through, all right, and I'm not going to go into a lot of detail over here. We're just going to talk generally through batteries. All right. I'm not going to do calcs, etc. Okay. We're just going to talk about Leclanche cells. All in your books, this is theory. This is called a dry cell because we use paste. At the anode, all right, we have zinc. So what are we saying? Zinc is going to do this, and we've got Zn plus 2 electrons. So the zinc is actually dissolving, isn't it? The zinc is going to dissolve. It's giving off and it's going into an ion form, and it's picked up on the other side. And no, you just have to check if you need to know this. 2NH4 aqueous plus 2MnO2 solid plus 2 electrons goes to 2MnOOH, all right, plus 2NH3. All right. Essentially, what are we talking about? We are talking about the cells. That's the cathode, by the way. We're talking about the cells that look like this. And you need to know that that's a carbon rod going down, and it's insulated. That's normally the positive, the under the negative. And this one over here, I'm just going to put a thingy. This has to be insulated. Okay. In other words, you want to keep your positive and your negative, because the positive is on the inside and the negative is on the outside. You want to keep the two apart in essence, right? You're then also going to get mercury cells, and many of those have been discontinued. Why? Because a mercury cell requires, or rather a mercury cell is toxic. Mercury is getting into the seas. Mercury is starting to contaminate many areas, tuna fish, etc., etc. And mercury being a heavy metal, there's pretty much nothing we can do with it. Well, I don't say that, but it sits in the flesh, apparently, of the animal that is consuming it in small quantities. Lead is equally toxic. I mean, lead pipes, etc., etc. Now, please understand that the above cells, okay, the dry cells, etc., are in effect, they are not rechargeable. They are not rechargeable. We never connect the cells that I'm speaking of now to a recharger. But we do get rechargeable batteries, a car battery. A car battery, it's called a lead acid battery for what we're going to study. And the lead acid battery, all right, the lead acid battery, you'll see now, the anode is basically like this. The lead is Pb solid plus HSO4 minus going to PbSO4 plus H plus 2 electrons. This is the anode, and the cathode is actually going to be PbO2, HSO4 minus plus 3 hydrogens plus 2 electrons. No, you don't have to know these to the best of my knowledge. PbSO4 plus 2H2O. All right. Now, this happens over here. This cell is when we are discharging. All right. And here, by the way, is the lead, and here is the acids portions of it. So this is the discharging situation over here, and the reverse reactions occur when car is running. Because when the car is running, the engine is turning over. The engine is using what? The engine, we know, is now becomes a generator, doesn't it? The engine starts generating. It actually becomes a dynamo. It charges up the cell. The engine uses gas, diesel, okay, to generate current. And that current, okay, and that current flows the opposite way to recharge. So when it's discharging is when we are starting the engine. And the reverse reaction is when it turns around. Okay? Then we get the nickel-cadmium battery. Okay? We get the nickel-cadmium battery, which is the last one, NiCad, like that, which is nickel and cadmium. All right? And that guy is, you need to discharge, that's a rechargeable battery. And basically the lithium batteries today as well, you get the rechargeables. Where do we use these nickel cadmiums? Small current, but it's a long life batteries. So you'd use them in things like calculators and things like that you don't want to change. Also, I think pacemakers use things like this. Not the rechargeable kind, but they're going to use the batteries that give us stable current for a long period of time. So these are rechargeable. The one thing that we say about these is you must allow full discharge before recharge. Okay? We say that at home to our kids. Please stop plugging everything in. When you see you've lost 5%, don't plug it in. Reason being is you are going to fry your battery over a period of time. Period. It's going to happen. You're going to lose battery life. Okay? And lately we know that the engineering in elements is not going to be there for 10 to 20 years. That would be if you bought let's say, a piece of huge mechanical equipment. Today's stuff very much, it lasts out your 2-3 years and then it changes. Why? Because the driver has now become the technology. More and more technology is being crammed into these devices that we use. That's life. That's the way it is. So that brings us to the end of that. The next section we're going to do is electrolytic cells, right? We're actually going to now start looking at industrial preparations. In other words, we're going to apply a current. These that we've spoken about now is chemical energy. This, let me just basically put this down as a last thing. What we have now discussed was chemical energy being converted to electrical, okay, energy. This is galvanic cells, aka batteries, right? The lemons and the zinc, copper, and the Leclanche cells, etc. That's what this is all about. Cheers, I'll see you in the next version. And that's pretty much going to take us through to industrial processes, which is where those of you who are going to go into Chem Eng are going to love it. Cheers, bye.